All right. So thank you, all of you, for joining for another season of Discrete Optimization Talks. Before we start with the talks, actually, I'd like to point out that this season there is a change in the organization of DOTS. We are welcoming a new member, Margarita Castro, sorry. She is taking over for Elias, and I am also taking a backseat to Sylvia and Margarita. So the two of them are going to be now the main hosts of DOTS. So this is my, who knows, maybe this is my final welcome. But I still plan to attend. I do enjoy these seminars for whatever reason. Please, if you have any questions, you can always direct them to any three of us, but Sylvia and Margarita will probably be the ones who will be responding a little bit more often from now on. And this includes if you have ideas of presentations or people that you'd like to see, or if you yourself would like to volunteer, we have a form on our website that you can submit, or you can email us either at any of our individual emails, and we also have a shared email, talks@discreteopt.com or .org.com, I think, .com, that you can reach all three of us at the same time. We have a very exciting season. We have four slots that we were able to squeeze in this season, and we're happy to start today with presentations by students. We have done this once before. This time we've decided to pick the students who are all, some of you might recognize how we picked them. They were picked as award winners from the mixed integer programming workshop. So we are happy to give a little bit of a bonus to the MIP workshop award winners by giving them this presentation. And if there's an opportunity in the future, maybe we'll continue that for all the students out there. Hopefully that gives you a little bit of an extra motivation to submit posters to next year's MIP, which will be happening in Connecticut, I believe next May. Okay, so without further ado, let me start with our first speaker, who is Dahye Han. Dahye Han is a PhD student in operations research at Georgia Tech, advised by Dr. Shantanu Day. Her research focuses on design analysis and design and analysis of algorithms for mixed integer nonlinear programming and applying advanced optimization techniques to domains such as power systems and structural engineering. She is also interested in leveraging machine learning as an auxiliary tool to support and enhance optimization methods. Dahye, the floor is yours.
Thank you, Alex, for the introduction, and hello, everyone. Today, I wish to share a joint work with my advisor, Dr. Shantanu Day, about strong branching in QCQP, and we call this extreme strong branching. So our work is really motivated by this one question. Since strong branching has been really successful in MIP, can we extend it beyond binary variables? Theoretically, this seems straightforward, but implementationally, it's not as straightforward. So when we consider branching on a continuous variable, which is also referred as spatial branching, we need to decide a branching point, which we want to call this alpha. And unlike MIP, where if you have a parent node and two child nodes where one of the variable is fixed to either 0 or 1, when we are branching on alpha, we are not fixing any variables to specific value, but restricting the upper bound and lower bound of this variable to be less than or greater than this alpha. This alpha can be any point between and including the lower bound and upper bounds of the branching variable. There has been some previous extensions of applying strong branching to continuous variable. And the first method includes pre-selecting alpha for each variable based on the convex combination of the middle point of the variable bound and the relaxed solution. Another approach formulates this selection of alpha into a max-min problem and tries to tackle it with machine learning method after some relaxation. For this work, however, we want to follow more closely to the classical strong branching and fully use the objective function value improvement. So what we propose is to really go crazy and explore choosing the right alpha and the right branching variable simultaneously. And let me first explain the general scheme of the extreme strong branching and move into the details. So first, let's consider the original non-convex nonlinear problem at branch and boundary node K. The problem is minimizing some cost function over a feasible region Pk. And let's define Rk to be a convex relaxation of Pk. So at node K, solving over Pk gives us an upper bound, and solving over Rk gives us a lower bound. And now let the Rk with xi less than or equal to alpha be the convex relaxation of the feasible region where Pk is intersected with xi less than or equal to alpha. So this is essentially the left side of the child node when we branch on xi on alpha. Similarly, we can define the right side of the child node with Rk with xi greater than or equal to alpha, like this. And now what we want to do is we want to explore a few points of alpha per each variable of xi, from alpha 1, alpha 2, to alpha m, where m can be like a number that we choose. So how do we select alphas to explore? Because alphas can be anywhere between the variable's lower bound and upper bound, and we have limited computational budget to explore alphas. So for this, we conduct a binary search relying on the following remark. So the remark goes as, if the relaxed problem of the left child node with xi less than or equal to alpha is infeasible or has an optimal objective value greater than the current best objective function value of the problem, then the lower bound of xi is at least alpha. If we briefly go over the proof, suppose the case when the problem is infeasible, which means that the relaxed set with xi less than or equal to alpha is an empty set. This means that the Pk intersected with xi less than or equal to alpha is also empty. So the optimal solution must be on the other side of the tree, which is the right child node. And on the right child node, the lower bound of xi is alpha. Now, suppose the other case where the objective function value over the relaxed set is greater than the best objective function value of the tree. So this means that the solution over the relaxed set actually has a higher value of the objective function than the true optimal solution. So if you let the objective with star be the true optimal solution of the problem, this is strictly less than the node's relaxation solution. So the relaxed set Rk with xi less than or equal to alpha cannot contain the optimal solution. So we need to look on the other side of the node, on the other side of the child node, which is the right node. And what this remark really provides us is the search direction for the alpha. So if we bump into one of these two cases, we no longer want to explore any alphas that is smaller than the current alpha, because we know that the lower bound of xi should be at least alpha. We have only discussed the remark for the left child node case, but similar result holds for the right node case, so that if the right node relaxation problem is infeasible or has an optimal objective value greater than the current best objective value, then the upper bound of the variable should be at most alpha. Now, let me briefly go over the algorithm. First, we have the input, which is the upper bound of the tree. For each of the variable, we will explore several alphas based on the binary search. And then we want to reduce the bounds of the variables whenever possible. We will then compute the geometric score for each alpha for the points that we explored. And the score is calculated as the multiplication of the improvements in the lower bound of the left child node and then the right child node. Now, let's go ahead and search for alpha for some variable, let's say xi. Let's assume that the currently xi is bounded between 0 and 1. In this figure, the x-axis represents the branching point, and y-axis shows the corresponding objective function value of the relaxed solution when we have branched on that point. The dotted line here represents the upper bound of the tree. And we first try to solve the right child node problem only. So this is minimizing the cost function C transpose X, subject to X being in the RK with Xi greater than or equal to alpha. Since we have the bound between 0 and 1, we start by solving the right child node problem at the middle point, 0.5. We also know that the current lower bound, which is 0, we know that the objective function value will be the same as the parent node's relaxation. So we can assume that this line at the bottom is the objective function value of the parent node's relaxation. Since it's 0.5, we see that the objective function value is below the tree's upper bound. So we want to move to the right and explore some value between 0.5 and 1. So we take the middle point 0.75 and solve for the right child node problem. Again, but this time we see that the objective function value is above the upper bound, which shows us that if we branch on any point between 0.75 and 1, the right child node lower bound will be above the tree's upper bound. So based on the remark that we just saw earlier, we can then reduce the upper bound of this variable to be 0.75. So in the third iteration, we will explore the value between 0.5 and 0.75 again, and we get a value that is also above the upper bound and further reduce the variable's bound. We decided to do it up to iteration 4. So far, we have solved only the right child node problem, so we move to solve the problem on the left child node. Similarly, we start at the midpoint, 0.5, but now we move to the left-hand side to 0.25. Since the objective function value is above the tree's upper bound, we can increase the variable's lower bound to 0.25. We don't want to explore any branching points below 0.25, so we take the midpoint between 0.25 and 0.5 and take 2 more iterations like this. But up until this point, we have obtained objective function values of the left child node and then the right child node for different alpha values except the midpoint 0.5. So to complete, we need to get the objective function values for the left child node and then the right child node for the branching points that were not considered before. But then, for example, we don't need to solve the left child node at 0.75 because we already know that the variable's upper bound is at most 0.265 over here. If we connect the dots, we can see this type of monotonically increasing or monotonically decreasing function. And the last step would be simply to select the variable and then the branching point that gives the highest score. But because extreme strong branching can be computationally expensive, we also considered a reliability version of it. So we first collect the information on the improvement of the objective function value, and then we estimate the improvement after some fixed number of iterations of extreme strong branching. But what we did is when we estimate the improvement, we used only the ancestry information. And what I mean by ancestry is that, for example, if you have this type of branch and bound tree, let's say up until depth 3, we wanted to extreme strong branching. So for nodes 1, 2, 3, 4, 5, 6, 7, we do the extreme strong branching. But when we come to, say, node 8, we no longer do extreme strong branching, but estimate the score for each variable based on the information that we have collected from node 1, 3, 5, which are the parents in that tree, but we don't include information from the other part of the tree. So let's move to the computational results part. We found that this extreme strong branching method is particularly effective on bilinear bipartite problems, such as pooling or model updating or water management problems. The standard form for the bilinear bipartite problems, we have two sets of variables, x and y, where only x variables and y variables interact with each other through the matrix QK. And we can always scale x and y to be in these 0, 1 box constraints with some affine transformation. Our first test instances are pooling problems where we want to minimize the cost of blending different raw materials while meeting the output demand and quality specifications. The benchmark branching rules we compared against our BLL, MW, and FM rules, which are taken from the last names of the author of these two papers, 2 and 3. And BLLMW, the first rule, chooses alpha as a weighted combination of the midpoint and the relaxed solution. And the FM rule, the second rule, chooses alpha in a way that balances the infeasibility of the two child nodes, but this rule does not consider the objective function value improvement. We have tested on total 32 instances in the MINLP library, where the small instances are with variables less than they're 40, and the larger instances are with variables over 40, but less than 100. We didn't necessarily compare it against the commercial solvers because they're highly optimized and engineered for these standard instances. So for most of the instances, they were able to solve this like within a second, although it explored a more number of nodes. But as we can see on the small instances, the benchmark rule actually performs slightly better by about 3 seconds. However, for larger instances, we see that the extreme strong branching, which is noted as ESP, and then the ancestry reliability branching outperforms the benchmark rules. And when we look at the number of the nodes, it is also quite evident that we are able to achieve the optimality with much fewer nodes. And even if we consider the fact that we are exploring about like 4 times more LPs, we're solving 4 times more LPs because we're doing these binary search exploration, then the BLLMW rule, this is much fewer nodes that we explore. Next, we have tested our method to model updating problem, which aims to minimize the difference between the as-built model and then the math model. These are much more difficult instances, so we have set a 1 hour time limit and compare the remaining optimality gap. And in the table, we see that despite Groby achieving the smallest gap for the first 2 instances, extreme strong branching outperforms for most of the rest of the instances. And if you also compare the number of the nodes in the tree, extreme strong branching get to these small optimality gaps via only very few iterations. So if we could engineer the implementation even more efficiently, maybe it can solve more nodes and reach even smaller gaps. For these instances, ancestry reliability branching were not that effective. And most of the gap improvements were made when we were first doing the extreme strong branching, and little improvements were made when we started estimating the scores. For these instances, we did not include the previous 2 benchmark rules because they didn't make any improvements in the lower bound. So to summarize, the extreme strong branching can really apply the successive strong branching in MILP to the nonlinear world. It exploits the bound tightening, which is key in solving the nonlinear problems. And despite some computational burden, extreme strong branching outperforms other rules and even commercial solvers for certain QCQP instances. So this concludes my presentation, and thank you very much.